Hello everyone. So this is the third video of section 1.2 and this video we're just going to reduce some matrices, solve some linear systems, and we're going to have a lot of fun doing it. So I just want to start out with this linear system here. Three equations: x1 minus 3 times x2 is equal to 5, negative x1 plus x2 plus 5x3 is equal to 2, and x2 plus x3 is equal to 0. So we now have some more tools at our disposal. We know how to put a matrix in reduced row echelon form, and we're going to do that in order to solve this system. So first we want to set up the augmented matrix for this system. And so I get that the augmented matrix is the following. And so now, remember, we want to go through the algorithm we had presented last time for calculating the reduced row echelon form. So first things first, we want to identify our first pivot. Column 1 is the first non-zero column. This one in the top left looks like a great option for a pivot. And so what we want to do is use this one, which will eventually turn into a leading one, to get rid of all of the non-zero entries in its own column below it. So notice here, I've got a negative 1 in row 2. So to get rid of that negative 1, I'm going to do row 1 plus row 2, and I'm going to replace row 2 with that row sum. 0, negative 2, 5, 7, and 0, 1, 1, 0. Row 3 is left unharmed. So, at this point, there are no more non-zero entries in the column below my first leading one, so I'm good there. So next, I want to move left and down and find the next possible pivot point. Remember, it can't be in column 1 or row 1, so it has to be one of these 6 entries. And this is a situation where, again, I see a nice 1 here. And so I might actually just pick that 1 to be my next pivot point. But so to do so, notice the pivot position it's going to be in is in the second row, second column, right? Because we want to work over one row and one column at a time, if possible. And so we want to put this pivot point in the leftmost and topmost spot. And so first thing I'm going to do is I'm going to swap row 2 and row 3 to get this 1 in the correct position. And now I want to clear all of the non-zero entries below this one. So I'm going to do 2 row 2 plus row 3. All right. So, do I have potential for more pivot points or pivot positions? I do. So now if I cover up column 1, column 2, row 1, row 2, I'm left with 2 non-zero entries, 7, 7. Thankfully, at this step, it's fairly simple. This leftmost 7 is going to be my next pivot. And so I just want to make it a 1. And so all I'm going to do is I'm going to divide row 3 by 7. To get the following matrix. Zero, zero, 1, 1. All right, so I've done all of the zeroing out when the leading ones are looking down. I've found all three of my leading ones. Next, we need to make sure that all of those leading ones can look up and see only zeros. So this will be done by two more operations. So we're going to do negative row 3 plus row 2. And then we're going to do 3 times row 2 plus row 1. And I get the following reduced row echelon form matrix. So notice we have row reduced this matrix to its reduced row echelon form state. And so remember now, this corresponds to the following system of equations, which is equivalent to my original system. And so what this corresponds to is a solution to this system of equations. So this solution of x1 equaling 2, x2 equaling negative 1, and x3 equaling 1 is a solution to the original linear system. All right, so as you can see, putting the matrix into reduced row echelon form is a very, very good way to solve a linear system. Some things to note about this, well, actually, one thing in specific to note about, well, two things. Yeah, sort of one related thing. This system had 3 variables and 3 pivots, and it had a unique solution. So what do I mean by this? Well, x1, x2, x3 are the 3 variables. And notice A has 3 pivot positions here, here, and here because we have 3 leading ones. So I also might put leading ones here as well. And notice in the reduced row echelon form, when we consider the system of equations that it represents, a leading one corresponds to a fixed variable, right? So every leading one here is fixing one of these 3 variables. And so you can sort of think of every leading one I have is going to fix a variable. So if I have as many pivots or alternatively leading ones as I do variables, that's when I get a unique solution, right? Where every variable is just immediately fixed and there's nothing I can do. So remember, for any system of equations, there's 3 possibilities for a solution. I could have a unique solution, infinitely many solutions, or no solutions. We've seen what the reduced row echelon form of a matrix looks like when we have a unique solution. Let's see what it looks like when we have infinitely many solutions. And so we're going to row reduce another matrix. And in doing so, we're going to solve the following system. All right. So we've got 3x1 plus minus 4x2 plus 2x3 equals 1, negative 9x1 plus 12x2 minus 6x3 equals negative 3, and negative 6x1 plus 8x2 minus 4x3 is equal to negative 2. And so, as is somewhat standard with these problems, the first thing we want to do is set up the augmented matrix. And now we're just going to row reduce. So this problem, I think, is unique up until this point in that we haven't yet seen a problem that we have to do a little bit of work right off the bat to get a 1 in our leftmost pivot position. But thankfully, that's not going to be terribly hard. And actually, so I kind of see what's happening here. So I'm actually going to wait to put a 1. No, let's put a 1 there. I kind of like that idea. So I want this 3 to be my first pivot position, right? So this is what I eventually, the spot in my matrix I eventually want to turn into my first leading 1. So let's go ahead and divide row 1 by 3. Remember, in the algorithm, in this step, you don't actually have to turn this entry into a 1 right away. And I decided to here just to remain mostly consistent, I think, with how I would normally do it. But sometimes I don't like to, especially if I see that a lot of fractions are going to pop up. I might be hesitant to. The reasoning for wanting to just immediately turn this entry into a 1 is it tends to be easier to figure out how to zero out the entries below it. But it's sort of just personal preference. There's no actually 100% correct way to get to the reduced row echelon form, just as long as you're doing correct row operations to do so. So now I want to zero out the entries below my first leading 1. And so I'm going to do 9 row 1 plus row 2 and replace row 2. And I'll start writing out what row 2 is going to be. And we can start calculating it as well. Notice that when I add 9 row 1 plus row 2, I just immediately get a row of all zeros. So we know we want to move that row to the bottom of the matrix. However, it's generally smart to just sort of complete one step at a time. So what I would do next is zero out this negative 6, and then move this 0 row to the bottom of the matrix if necessary. But as we will see in a second, it might not be totally necessary. So now we want to zero out that 6, so I'm going to do 6 row 1 plus row 3 to replace row 3. And you might see what's going to happen here. So it turns out that the third row also is just a row of all zeros. So by eliminating these 2 entries below the 1, we're done. We've put our matrix in reduced row echelon form. That is because I have 1 leading 1. It looks down and up. It sees only zeros. No other leading entries. All of the 0 rows are below non-zero rows, and so we're good. So this augmented matrix corresponds to the following 1 equation. And so now we have 1 equation and 3 variables. 1 pivot position and 3 variables. 1 leading 1 and 3 variables. So we've got 3 variables and 1 pivot for leading 1. What does this mean? Well, notice, given this 1 equation, you could give me any value you wanted for x2, x3, and then I could find a correct value for x1. So let's say x2 was equal to 1, and x3 was equal to 2. Now that's too easy. Let's say x3 was equal to 3. then we would get 4/3 plus 2 is equal to 1/3. X1 is equal to 5/3 minus 2. And so x1 is equal to negative 1/3. But notice I could have alternatively chosen 3 for x2, 4 for x3, and still gotten a value for x1 that satisfies this one equation. And so there are infinitely many solutions because I have infinitely many choices for 2 of these 3 variables. So we generally will call variables that don't correspond to a pivot free variables. So they are free variables because they do not correspond to a pivot column. Or leading one, whichever you prefer. And so, if I have a free variable, then my system has an infinite number of solutions. And so specifically, if I have fewer leading ones than I do variables, at least one of those variables is going to be a free variable. And anytime I have a free variable, that sort of just inherently means I can set that variable to be whatever I want and still come up with a solution to my system, meaning that my system has an infinite number of solutions. So, last but not least, I want to look at what happens when we see no solutions. This won't be quite as involved. I just want to give you a matrix that is technically in reduced row echelon form. Look at its corresponding system of equations, and then discuss exactly what property of this matrix causes it to have no solution. So this matrix is in, not quite in reduced row echelon form. This matrix is in reduced row echelon form. Why is that? Well, leading 1, 0 is below it. Leading 1, 0 is above it, so we're good there. No non-zero rows, we don't have to worry about that. And so notice here we're good. So, and obviously both of our entries are leading ones. And so if we look at the system of equations that this matrix is the augmented matrix to, well, it would be x1 plus 2x2 is equal to 0. This last row, though, would be 0 is equal to 1. And, of course, that's not true. And so while this matrix is in reduced row echelon form, this corresponds to a system of equations that is just inconsistent, right? It doesn't have any solutions. And so, like we discussed last time, this has the dreaded sort of 0, 0, 0, 0, 0 non-zero row that we don't want to see. And so we can actually summarize this phenomenon in a theorem, which will end the video today, that a linear system is consistent, meaning it has at least one solution. If and only if the rightmost column of the augmented matrix is not a pivot column. And so this means, of course, that we will not get something like this, where I'll draw that a little more clear. This means that we won't get any row in the reduced row echelon form matrix where I have all zeros and then a non-zero entry at the end, right? And so notice if the rightmost column of the augmented matrix is a pivot column, then it's going to have a leading one. And so actually specifically in the RREF, we get 0, 0, 0, 0, 0, 0, 1. So that will wrap up section 1.2. Thanks for watching, and yeah, nothing else to say for now.